Have you ever wondered how an AI gets language? You know how it understands nuance or even poetry? Well, it's not magic, though it sure can feel like it. It's actually mathematics. We're going to dive into the core concept that gives AI its power, something called embeddings. Think of it as the secret language that machines use to make sense of, well, pretty much everything. To kick things off, let me throw a bit of a riddle at you. It sounds more like a word puzzle than a math problem. What do you get if you take the concept of a king, subtract the concept of a man, and then add the concept of a woman? The wild part is a computer can solve this, and how it does it is just fascinating. And there it is. The answer is queen. Now, for us, that kind of makes intuitive sense, right? It's a leap of logic we can make pretty easily. But for a machine to do that, that shows a really deep understanding of relationships. And this little piece of computational magic is the perfect way to start unpacking exactly how a machine can perform this kind of, well, conceptual algebra. At the very heart of all this is the idea of an embedding. And really, it's just a translation. We take something messy and human, like a word or an idea, and we convert it into a simple list of numbers, a vector. That's it. That's how AI takes our abstract world and organizes it into the language of math, something it can actually compute with. A really great way to picture this is to imagine a giant, sprawling map of meaning. Every single word or concept you can think of has a specific point on this map, kind of like its own unique set of coordinates. And here's the cool part. Words with similar meanings naturally end up clustered together in the same neighborhood. Now, what's so cool about this map is its axes. Instead of your typical north-south or east-west, the axes represent abstract concepts. So you might have an axis for gender or royalty or even formality. And as you can see, the vector, the direction and distance from man to woman, is almost identical to the vector from king to queen. It's this spatial relationship that lets the AI solve our riddle. It's all just vector math. You know, this isn't even a new idea. Way back in 1957, a linguist named J.R. Firth laid down the philosophical bedrock for all of this. He basically said that a word's meaning isn't just its dictionary definition, it's defined by the other words that consistently show up around it. And that simple, elegant principle is what guides how AI learns language today. This idea has a formal name, the distributional hypothesis. It's the core rule that AI models use to build their maps of meaning. So if words like dog and puppy are always popping up in sentences with words like walk, fetch, and loyal, the model starts to figure it out. It says, hey, these two must be related, and it places their vectors really close to each other on the map. Okay, so that's the theory, and it makes sense. But how does this happen in practice? What are the actual mechanics? How does a model read billions of sentences from all over the internet and turn all that statistical information into this neat geometric map of meaning? Well, there are a couple of ways, but two of the classics are RITEC and Glove. RITEC is clever. It learns by looking at a word's immediate neighbors in a small window of text. It's very local. But Glove, which stands for global vectors, takes a different path. It builds its understanding by analyzing word co-occurrence statistics across the entire set of text, giving it a powerful, big picture view of the language. The real genius of Glove is that it focuses on the ratios of how often words show up together. For example, the probability of seeing the word solid near ice is really high, but the probability of seeing solid near steam is really low. That ratio between those two probabilities is a massive signal that encodes the relationship between ice, steam, and the concept of solidity. To quantify this, models use a statistical measure called point-wise mutual information, or PMI. It's just a formal way of asking, how much more often do these two words appear together than we'd expect by pure chance? If the answer is a lot, they get a high PMI score, and that tells the model these words have a strong relationship. This is the raw data for building the map. And this is the master blueprint. Now, don't worry about the equation itself. Just think of it as the Glove model's ultimate goal. It's a puzzle it's trying to solve. By working tirelessly to find the lowest possible value for this function, it learns the perfect vector coordinates for every single word, making sure all those relationships are reflected perfectly on the map. Okay, that was a lot of theory and math. So why do we bother with all this? What's the real superpower that this whole process unlocks for AI? This is where embeddings go from being a clever trick to a truly foundational technology. Part of the magic comes from a mathematical principle with a very long name, the Johnson-Lindenstrass lemma. but what it does is pretty amazing. It basically guarantees that we can take an incredibly huge, high-dimensional dataset and shrink it down into a much smaller, manageable space without losing the essential relationships between the data points. This is what makes real-time AI feasible.
So the payoff is huge. First, this makes computations that seemed impossible possible. Second, it allows for incredibly rich representations. We can pack abstract concepts like whimsical or Hitchcockian into these compact vectors. Third, it enables something called transfer learning. We can reuse these pre-trained language maps for totally new tasks, saving a ton of time and resources. And finally, this is the engine that powers the search engines, recommendation systems, and chatbots you use every single day. So when you get right down to it, embeddings are more than just a data processing trick. By turning our world into vectors and placing them on this map of meaning, we're giving AI the tools to understand the fundamental relationships that connect not just our language, but maybe even our reality.
And that leaves us with a final, pretty mind-bending thought. We've managed to successfully map the vast, complex world of human language. So what's next? What other abstract concepts, emotions, scientific theories, artistic styles could we translate into a geometric space for an AI to explore and understand? The possibilities are truly staggering to think about.